55 present, sir.
So I would request all the participants to open the camera. We have been joined by our chief guest today, keynote speaker, Professor B.N. Dole, sir, who is currently Director, Board of Exam and Evaluation of Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhajinagar. Also, he is a former head Department of Physics of our university. So I welcome Dr. B.N. Dole, sir, on behalf of this entire group of 33rd NEP Orientation and Sensitization course. So I would request all the participants to open the camera. सभी सहभागी participants कैमरा ओपन करें. सभी लोग मैंडेटरीली कैमरा ओपन रखें अपना इनॉग्रल के लिए. इनॉग्रल और वैलिडिटरी दोनों भी सेशन में आपको कैमरा ओपन रखना है. बाकी के सभी सेशंस में आप कैमरा बंद रख सकते हो. अपना माइक म्यूट हमेशा रखिए. It is a personal responsibility of the participant that his or her mic should be muted. No disturbance should be there because of your mic in the classroom. Kindly take a note of it. So I would request all the participants to open the camera. And I would request Gaurav to start the university song and the banner.
गीत आमुचे
जागराचे साचे जनमनाचे गीत आमचे जागराचे गीत आमचे आकाशाचे गीत आमचे सागराचे इतिहासाचे जनमनाचे गीत आमचे जागराचे
अभंगाचे ओवीचेही माय बोलीचे माहेर
वाऱ्यातले मराठीचे दिवे लख घरोघर संतांचे विरागी गीत आमचे कातळाचे इतिहासाचे जनमनाचे गीत आमचे जागराचे तंतु तंतु संघर्षाचा पैठणीत भिनलेला
नक्षीतच पक्षी पक्षी विजयाचा विरलेला
सोन पहाट उदयाचे गीत आमचे उजेडाचे इतिहासाचे जनमनाचे गीत आमचे जागराचे प्रज्ञेचा सूर्य नवा शब्द शब्द उजळून गेला समतेचा संगराचा अर्थ ढाळून गेला विराट विशाल संस्कृतीचे गीत आमचे जीवनाचे इतिहासाचे जनमनाचे गीत आमचे जागराचे गीत आमचे आकाशाचे गीत आमचे सागराचे इतिहासाचे जनमनाचे गीत आमचे जागराचे
So thank you, Guru. You can stop the university song. So on behalf of UGC Malviya Mission Teachers Training Center, Dr. Babasaheb Ambedkar, Marathwada University, Chhatrapati Sambhaji Nagar, I welcome today's chief guest, inaugurator for this afternoon session, Professor B.N. Dole sir, who is also the Director, Board of Exam and Evaluation of our university. Also, he is a former head professor and head of Department of Physics of our university, a person with a vast teaching and research experience. Also, he has been awarded as an ideal teacher by our university way back in the year 2015. He has a collaboration with CMET, Cherapalli, Hyderabad, Tata Institute of Fundamental Research, Kolaba, Mumbai, Inter-University Accelerator Center, New Delhi, UGC DAE CSR, Ahilya Devi University Campus, Indore, and UGC DAE CSR, Bark, Mumbai. Also, he has a vast teaching experience, right from a research assistant to the senior professor in our university. Also, he has headed Department of Physics and also was in charge of condensed matter physics laboratory of Department of Physics. Also, he has been warden, worked as a warden program officer of NSS PG unit. Also, he has been a chairperson
ठीक
for
है
various Board of Studies in Physics way back in the year 2023. Also, he has been in charge head department of electronics of our university. Under his able guidance, many students have been awarded PhD, and he has successfully completed many research projects with a total outlay of 41 lakh 93 thousand. Also, he has international linkages with Dr. A. Branwo, Moscow University, Moscow, and also an MOU with Dr. Stalos Ilias, Department of Electrical Engineering Technology Education Institute of Western Greece. Also, he has been affiliated as a member, reviewer, and chairperson, and he has also coordinated many activities and also board of examiner, and also have worked on various research projects also. So, on behalf of this entire group, again, I welcome Professor B.N. Dole, sir. So, this 8 days NEP orientation and sensitization course, which is the 33rd NEP and orientation and sensitization course being organized by this UGC Malviya Mission Teachers Training Center. And today we have Professor B.N. Dole with us. So I would now request Professor B.N. Dole to deliver a short inaugural address to all of us. Over to you, sir.
Yeah. Thank you, Assistant Director and my friend Muhammad Abdul Rafe sir, and the Director of UGC-MMTTC, Professor Dhanasri Mahajan, Madam. Thank you because you have given a very nice introduction, and it is a very short. And today, when I reported to this MMTTC, that is Mission Malviya Teacher Training Center, and I came to know that because we have to conduct this session, and the responsibility on my shoulder is that to inaugurate. This is the first. The second one is to engage the lectures. Now, first of all, because as we know that the MMTTC running the many sessions, but this is the double digit and double three NEP orientation and sensitization, MMC, this sensitization and the inaugural function, that responsibility is assigned to me. I'm very happy because as we know that the main function and the task of this center is to convey the message. Another one is to organize the sessions, and through the sessions, the information, effective, qualitative information should be furnished among the teachers, among the professors through this center. The role of this center is a very pivotal and important in this region, not only in the Marathwada, but all over Maharashtra and India, because this is the double three, that is the 33 NEP orientation and sensitization. Through these sessions, so many professors assistant professors and associate professors, particularly the assistant professors and associate professors get benefited. And therefore, I am very happy to announce that I declare this inaugural function, I declare it is inaugurated. Now, the another responsibility is that because I have to again engage the lecture, and the topic of my lecture is that the advanced materials for futuristic applications, its innovations and opportunities. Now, this topic is a little bit quite hard, but you see, there is no life without material. There is no, as I mentioned, there is no life. There is no human being without the material. And everywhere you will find the material. And therefore, I used to say that a life is incomplete without material. No life is complete without material. So, even though the major role of the materials in the life is every day, and therefore I said that one, the which type of materials, and they play the pivotal role in the society, in the among the people, among the nations. So you can understand that one, and therefore the title of my topic is the advanced materials, futuristic applications, and is there a possibility to find the new materials and their innovations, their means the discoveries and findings. And if we find the new materials, then again, what type of opportunities? Okay, because you see, across the globe, as I said, if there is no material, then the life, that would be the no life. There will be no life. If there is a no life, then means you see. So therefore, I say this is the important, very, very important. Without the material, one cannot alive. And therefore, you see, this talk without this PC not possible. If I don't have the pen drive, then this is not possible. Even though you people sit over there, means at various places, without the chair, without the table, it is not possible. Now, so therefore, I used to say, without the material, the life is not complete. And therefore, now the main and important responsibility, very important responsibility is on our shoulder, that we have to find the materials. Those materials are in existence, no problem. They are giving their applications. We are utilizing their applications. We are finding their applications, but those materials are unknown still yet. We have to find the new materials. And therefore, if we find the new materials, I mean, here some nanomaterials are there, some composites are there. Even though you people can understand that in a simple language, that is graphene oxide from the graphite. In 2010, the Jim and No Solo found that. So up to 2010, the structure of the graphene was unknown. Okay, it was not known. And in 2010, they told the structure of the graphene is honeycomb, okay, urzite. And therefore, they recipiented the Nobel Award on that. You see, recipiented the Nobel Award only due to that. The what is the structure of the geo up to 2010? It was unknown, but they said its structure is honeycomb, and they got. You see the material and its importance means without the, as I mentioned that one, if there is no suppose the wheat, gehu, chapati, it is also the material, and we use that one to alloy even the water. It is a liquid, but it is also material. So all these things, which even though is salt, it is also the material, and we use all these things so for the eating purpose. But in another case, if you see, we carry the books, we carry the pens, all these things, these are the materials, and without that one, our life, even though while walking we use the shoes, okay, chappal and all these things. So come to this, and therefore my intention is that the topic, my title is this one, and that is very, very effective. I would like to say the life, the advanced materials for future. What is the importance of this? Now, after this, you will come to know that if I touch to the slides, and then you will find, yeah, okay. Now you see the rapid advancement of science and technology has significantly increased. Okay. Oh. Just a minute. He, they should. Now you see the very vast advancement of S&T, that is the science and technology, significantly enhanced the demand for high performance, okay, high performance materials with superior properties. Advanced materials including nanomaterials, functional composites, metamaterials, and smart materials are revolutionizing various industries, from energy storage to biomedical applications. These materials exhibit unique mechanical, electrical, optical, and chemical properties, making them essential for next generation technologies. Now you see these materials, advanced materials, that is the nano, functional, meta, and smart, revolutionizing so various industries, from energy storage to biomedical. Okay, now you see energy storage. Is it possible to store? These materials play that role, and I'm sure energy will be stored, and whenever and wherever we require, we'll use that one. Therefore, these materials outline the unique mechanical, electrical, optical, and chemical properties. Mechanical, electrical, and optical, essential for these materials. Which materials? These materials, nanomaterials, functional, composites, metamaterials, and smart materials. These materials are, okay, they have the unique properties, that is optical, mechanical, electrical, chemical. And these materials are very important because the making them essential for next generation. This presentation outlines the latest innovations in advanced materials, focusing on emerging trends, fabrication techniques, and novel applications. Okay. Now, here the important aspect is that again the commercialization and industrial adoption opportunities is there. Yes, and the issues will be addressed: its scalability, cost effectiveness. So if these materials are applicable and these materials, so for the next generation, then what is again important, if it is not affordable, if we develop the product and it is not affordable, then what is the use of that? So again, the cost effectiveness plays pivotal role. Sustainability, okay, and these are, so for the industry, okay, commercialization and industry adoption opportunities, addressing scalability, cost effectiveness, and sustainability challenges. The key topics of this one can cover, and these key topics covered, including the materials, graphene, MGen, and transition metal diluted. Okay. For energy storage, photocatalysis, flexible electronics, and sensors. So these materials, okay, means for energy storage, these materials, MGen, graphene, okay, and photocatalysis, flexible electronics and sensors, nanocomposites, and hybrid materials for enhanced mechanical and thermal performance. So nanocomposites and hybrid materials for enhanced mechanical and thermal performance. So enhance this. Metamaterials means nanocomposites and hybrid materials for enhanced. These materials means nanocomposites and hybrid materials enhance the mechanical and thermal performance of the material. These materials enhance the mechanical and thermal performance. Metamaterials for photonics, electromagnetic wave manipulation, and stealth applications. Bio-inspired and smart materials for biomedical, self-healing, and adaptive technologies. Sustainability challenges and the role of advanced materials in achieving a greener future. Okay. Sustainability challenges and the role of advanced materials in achieving a greener future. Now see here the CNT, nanospheres and clusters, classified the nanomaterials based on their, means nanomaterials are classified based on their dimensionality. Here 0D, 1D, 2D, I mean dimensionality, 0 dimensions, 1 dimension, 2 dimension, and 3 dimension. Now the Zero dimension, these are the nanosphere clusters, namely the quantum dot fluorines gold nanoparticles. Okay, means quantum dot fluorines and gold particles, gold nanoparticles. These are zero dimension, means nanosphere. Now, one dimension, that is the wires, rods, tubes, okay, rods, tubes, and wires. Okay, these are the means one dimension, rod, tube, wire, rod, tube. Okay, this is a rod, this is a tube, and this is a wire. Means one dimension, rod, tube, wire. Two dimension, thin films, plates, layered structures. This is a thin film, sheet, graphene sheet, layered nanomaterials, two dimension. Three dimension, bulk nanomaterials, polycrystals, liposome, polycrystalline, and dendrimer. Means liposome, polycrystals, polycrystalline, and dendrimer. Okay, the bulk materials, nanoparticles. Means here the zero dimension, the nanoparticles, your nanomaterials classified based on, these are classified based on dimensionality. And zero dimension means the sphere, fluorines, quantum dot, and gold nanoparticles. This is a zero dimension. One dimension, rod, tube, and wire. These are one dimension. Two dimension, plates, films, and layer structures. And three dimension, bulk nanomaterials, that is polycrystals and polycrystalline. Okay. What are advanced materials? Again, we are going to touch this topic. Title of the topic is Advanced Materials. Advanced materials, this is referred to engineer substances with superior properties. Okay. So here the advanced materials refer to engineered substances with superior properties to conventional materials, making them suitable for high performance applications across various fields. These materials exhibit exceptional characteristics such as high mechanical strength. First of all, we will understand that, and you people will understand what are advanced materials. I'm in lecture. So here, engineered substances with superior properties. The substances are engineered and they carry the superior properties to conventional materials, making them suitable for high performance applications. Means what are the advanced materials? The materials here, material means substance engineered, and they have superior properties. If the materials, substances, engineered substances with superior properties to conventional materials, making them suitable for high performance. These means superior properties, engineered substances with superior properties to conventional materials, making them suitable for high performance applications. Means these advanced materials are suitable for high performance application. They have the high performance applications across various fields. These materials exhibit exceptional characteristics such as high mechanical strength, electrical conductivity, thermal stability, optical tunability, and chemical reactivity. These materials exhibit exceptional characteristics. These materials show exceptional characteristics, and that is high mechanical strength. They have electrical conductivity, thermal stability, optical tunability, and chemical reactivity. First of all, one must understand the engineered substances with superior properties to conventional materials, making them suitable for high performance applications. And therefore, these materials, see, very important aspect, because the material, these materials show the exceptional characteristics such as high electrical properties, high mechanical strength, electrical conductivity, thermal tunability, stability, and optical tunability. Means thermal stability and optical tunability and chemical reactivity. These materials have. Why these are the extraordinary? Therefore, this example include nanomaterials, that is the graphene and MGENs, high entropy alloys, metal organic framework, perovskite, and bio-inspired materials. Their unique properties enable their use in energy storage, environmental remediation, biomedical applications. Their unique properties enable their use in energy storage. Graphene, MGEN, high entropy alloys, metal organic framework, MOF, perovskites, and bio-inspired materials. Their unique properties enable their use in energy storage. Okay, of these materials, their use in energy storage, environmental remediation, and biomedical applications, and next generation electronics. Emerging trends in advanced materials. 2D materials, that is graphene, MGEN, and transition metal divalent. Okay. So these materials, high electrical, they have, as I mentioned, high electrical and thermal conductivity, two-dimensional materials, mechanical strength, means electrical, thermal, mechanical strength, and again, the another important aspect is that the surface area plays again a very important role. That is the surface area. What are the applications these materials possible application? That is the energy storage, flexible electronics, and sensors. Now the here nanocomposites and hybrid materials combining nanomaterials and polymers. Okay, these are the nanocomposites and hybrid materials combining nanomaterials with polymers, metals, or ceramics for tailored properties. See here, this is a nanocomposite and hybrid materials, nanocomposites and hybrid materials combining nanomaterials with polymers, metals, or ceramics for tailoring the properties. Now, its application is structural materials, coatings, and biomedical uses. Nanocomposites and their applications. These materials are being used for the coating and biomedical applications. Okay. Now, metamaterials, two-dimensional materials are used here, and therefore the metamaterials engineer to manipulate electromagnetic waves, negative refractive index, photonics, cloaking, and wireless communication. Smart and bio-inspired materials, self-healing, shape memory, and biometric materials inspired by nature, wearable technology, robotics, and medical devices. These materials. Now you see, these are the materials for energy, 2D dimensional materials. 2D materials are being used for the energy storage, for the fabrication of sensors and flexible electronics. Now, nanocomposites and hybrid materials combining nanomaterials with polymers, metals, and ceramics for tailored properties. Smart and bio-inspired materials, self-healing, shape memory, and biomimetic materials inspired by nature. And these are for wearable technology, robotics, and medical devices. Now you see the material class and examples. Oxides. These are the TiO2, titanium dioxide, zinc oxide, iron oxide, tin oxide. These are the oxides and they are used here. Now sulfides, MOS2, WS2, ZNS, CDS, SNS2, copper sulfide, lead sulfide, molybdenum diselenide, tungsten diselenide, zinc selenide, cadmium selenide, lead selenide, and copper selenide, tellurides. This is the classification, means material class, and these are the materials. Now, tellurides means this is a bismuth telluride, antimony telluride, molybdenum telluride, and this is the tungsten ditelluride, lead telluride, and cadmium telluride. Nitrides, boron nitride, gallium nitride, aluminum nitride, tin nitride, silicon nitride, zirconium nitride. Carbides, titanium carbide, silicon carbide, tungsten carbide, zirconium carbide, and tantalum carbide, niobium carbide. Borides, titanium diboride, zirconium diboride, chromium diboride, hafnium diboride, phosphides, gallium phosphide, indium phosphide, zinc phosphide, material class, and their examples. Okay. Now, see, these are the materials here. Okay. Dimensionality, an example. We studied that. Nanospheres, that is the fullerene, quantum dot, and gold nanoparticles. These are the examples. Nanoparticle with all dimensions confined at the nanoscale, leading to unique optical and electronic properties. Now, one-dimensional carbon nanotubes, tubes, rods, and means tube, rod, and wires. That these are the means CNT tubes, nanowires, silicon, zirconium, zinc oxide, gallium nitride, and molybdenum sulfide, disulfide. Nanorods, materials with one dimension significantly larger than the other two, exhibiting high aspect ratios and excellent charge transport properties. Okay. Now, two-dimensional materials, we studied that one. Particularly, two-dimensional means thin films. Okay, thin sheets, thin films, and multi-layers. That is graphene, EMGen, phosphorane. These are the two-dimensional. Automatically thin materials with strong in plane bonding and weak van der Waals interaction between layers, leading to exceptional mechanical, optical, and electronic properties. So these are the automatically thin materials with strong in-plane bonding and weak van der Waals interaction between layers. Okay. So two-dimensional means optical, exceptional mechanical, optical, and electronic property. And this is the MOF, metal organic frameworks, covalent organic frameworks, perovskites, bulk metals, polycrystalline oxides, three-dimensional metal organic framework, barium, titanium, and bulk materials. Okay, materials with all three dimensions extending in space, providing structural integrity and diverse functionalities for various applications. Synthesis technique, now you see, means the materials and their classifications, and these materials classified based on dimensionality. Okay, means the material class based on dimensionality, and we studied that the dimensionality. Okay, now the classification, materials are classified, and now we came to know that the zero dimension, particularly with the example, that is the quantum dot, gold nanoparticles, and fullerenes. These are the zero dimension. One dimension, rod, wire, okay, rods, wires, these are the one dimension. Two dimension means the thin films, sheets, means now you see one dimension, wire, rod, and tube also, but in two dimension, films, sheets, okay, and three dimension, that is the polycrystals, and these polycrystals, okay, means we came to know that this is the classification of the material. But again, the important aspect is lagging here, and that is which one? You can now, you see, classification we done, we know now, that is the introduction part, in that we studied that one. The materials are classified on this. But after the classification, how one can synthesize these materials, and after synthesizing, one can confidently say this material is belong to this class. That is again, and therefore the synthesis technique for 0, 1, 2, and 3 dimensions materials. Okay. Now there are there are the diverse techniques to synthesize these materials, and these diverse techniques, methods are also outlined on this slide. Now you see the one by one, the co-precipitation method is there, CBD is there, Silar technique is there, Sol-Gel method, and CVD, chemical vapor deposition, electrochemical and electrophoretic technique method, Hammer's method, and hydrothermal method. These methods play a very pivotal role for synthesizing the materials. One by one now. Co-precipitation method, and this method is specially and particularly used for the synthesis of 0 and 1D nanomaterials, nanoparticles. That is, this method used for the synthesis of particularly zinc oxide nanoparticles. Principle here of this method is given, and that is, it involves the chemical precipitation of Zn2 plus ions using a precipitating agent, that is the sodium hydroxide, NH4OH, and this reaction leads to the formation of zinc hydroxyl group with which decomposes into ZnO. Now, involves the chemical precipitation of zinc ions. Now, ZnO synthesis using the co-precipitation. Precipitate of Zn2 plus ion solution, that is, we have to dissolve the zinc nitrate in deionized water, and the precipitating agent, so that is the sodium hydroxide, under stirring, formation of zinc hydroxide precipitate, white precipitate forms here. Deionized water was used, and then aging and washing. Now it's settled, wash with ethanol and water. So drying calculation, heat at 400 to 600 degrees Celsius to obtain zinc oxide nanoparticles. Now this is the pictorial diagram of the synthesis of ZnO by co-precipitation method, and here is the zinc chloride, zinc dichloride. Adding zinc dichloride in deionized water, mixing the solution by stirring for 30 minutes at 40 degrees Celsius. Bearable temperature. And this is the, now adding sodium hydroxide in deionized water, mixing the solution by stirring for 60 minutes at 40 degrees Celsius. Mixing the solution by stirring for 60 minutes at 40 degrees Celsius. Now you see here stirring, mixing the solution by stirring for 30 minutes. And here is period, double the period. But temperature is same, only period is enhanced for adding this sodium hydroxide in deionized water. Now here the zinc dichloride, and this is the sodium hydroxide solution poured dropwise into prepared zinc chloride homogeneous solution. Now obtain precipitate here. Obtain precipitates were washed several times with ethanol and DI water. Now this means here we obtain the precipitate, and this precipitate was washed several times by again the DI and ethanol. So dried precipitate were annealed at 500 degrees Celsius for 2 hours. Now you see, when we get the precipitate, because the zinc chloride and NaOH, okay, zinc chloride and NaOH. So NaOH and zinc chloride, these two solutions mixed separately in DI for 30 and for 60 minutes respectively at static temperature 40 degrees Celsius. And these two solutions were poured into a single beaker, okay, NaOH solution poured dropwise into prepared and zinc chloride homogeneous solution. Then here the precipitate was obtained and it was washed several times with ethanol and DI. Dried precipitate were annealed at 500 degrees Celsius for 2 hours. And now you see, dried precipitate was annealed at 500 degrees Celsius for 2 hours, and we got the zinc oxide nanoparticles. Now you see. Now here, from the why we use the co-precipitation method to get the nanoparticles, zinc oxide nanoparticles. Now another method is the chemical bath deposition method. Okay. That was used for the 0 and 1. And this is for 1 and 2. Means chemical bath deposition method is used to synthesize means 1 and 2 dimensional nanostructure materials. It means the carbon nanotubes, wires and rods, and thin films and thin sheets. Okay. Now the principal controlled chemical reaction in an aqueous solution forms a thin film on a substrate. A controlled chemical reaction. Now the TiO2 thin film synthesis using CBD, chemical bath deposition, thin films, means two-dimensional materials or films can be tailored or engineered. Preparation of solution. Dissolve the titanium, this chloride or titanium sulfate, disulfate in water. This is we have to dissolve the titanium tetrachloride or titanium disulfate in water. Addition of complexing agent. Add this. This is the NH4OH. Okay. To control pH means this substrate ammonium hydroxide to control pH, substrate immersion. Now dip the glass or this FTO substrate. Now this deposition process, titanium oxide nanoparticles nucleate and grow. Annealing and characterization. Heat at 450 degrees Celsius for phase conversion. Now this is the overall procedure. This is the procedure of how the thin film can be synthesized. And here is this is the substrate. Okay. This is the retort stand. It is fixed here. This is this one. And this is the substrate. Okay. This is the thermometer. Now these are the beakers. All these. Now Silar technique, a Silar method. What is this? Now you see flow chart for titanium nitride synthesis using Silar. Means here cationic deep substrate dipped in titanium tetrachloride solution, rinse with water, remove excess precursor, anionic deep substrate dipped in ammonium hydroxide for reaction, repeat steps 1 to 3 times, multiple cycles for uniform film growth. Now annealing, heat at 500 degrees Celsius in nitrogen atmosphere. Now you see, this is the bare glass substrate. Now adsorption of this. Here is again this process, means this substrate. This is the bare open glass substrate. Put means clean using the cationic. Okay, means absorption of cations on this bare glass. Now here are the cations. Now again washed with the distilled water. Again after removal of loosely bound cations. So some loosely bound cations removed. Again, now loosely means these are the loosely here and these are bound. Okay, bound. Now again anionic precursor. Here this solution means this substrate which are the cationic means anionic now, and here some again loosely packed cations are removed and some anionic they are stick on this. Now you see here are some ions are also loosely packed, they are removed, and now you see the order. This is this one, migration. Now the fourth one is the Sol-Gel method. And this is also the versatile method because this method is used for 0 dimension, 1 dimension and 2 dimension. Means if you see the previous three, particularly one is used for the 0 and 1, another one is the 1 and 0, okay, 1 and 2, and the third one was also for means 1, 2, but this is for 0, 1 and 2 dimensional materials. Example is titanium oxide nanoparticles. Principle of this method is a colloidal solution undergoes gelation to form a network gel, which is then dried and calcined to get nanoparticles. Now, the flow chart of this is given as under, and that is like this. Dissolution of titanium precursor in isopropanol, hydrolysis and condensation, while water and acid catalyst, Sol-Gel formation. The name of this method is Sol-Gel. Allow slow polymerization, aging and drying, remove solvent, calcination, heat at 500 degrees Celsius to crystallize titanium dioxide. Okay. So this is the calcination, heat at 500 degrees Celsius. Now this is the flow chart of this one. And this is the nanoparticle synthesized using this. Okay. Means this method is generally means acetic acid 2.5 ml and so heated up to 500 degrees means at 500 degrees Celsius, sorry, at 5 hours, for 5 hours stirred here. Now the 80 degrees Celsius, 1 hour stirring here. Okay, acetic acid here, nitric acid is here. Okay, acetic acid, nitric acid, naturally cooled room temperature. And here is white precipitate, convert into white solution. Okay. Means this, first of all, isopropanol 6 ml. Okay, and this material, titanium dioxide nanoparticles, means after that titanium nanoparticles, titanium oxide nanoparticles after heating, means from this one, then this TT means isopropanol titanium, and stir this one, add dropwise distilled water 75 ml, white precipitate. Here we got, here was no, but here is this. Now stirred, then acetic acid 2.5 ml, 5 gram stirring, nitric acid 1 ml, 1 hour stirring, naturally cooled room temperature, and this is the vacuum dry 60 degrees Celsius, at 60 degrees Celsius. Then the material annealed at 500 degrees Celsius for 3 hours, and we got the titanium oxide nanoparticles. Now chemical vapor deposition, fifth route is this one. used for one-dimensional and two-dimensional materials. Titanium nitride nano structures. Okay. Hello. हो सर, नमस्कार. सर मी एका ओरिएंटेशन कोर्सच्या लेक्चरमध्ये अर्जंट आहे काही. टेक्निकल सेशनला. हो 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 हो. अच्छा म्हणजे हो ना हो ना हो ना हो ना. मी सांगतो सर तुम्हाला संध्याकाळी. का आता तुम्हाला टाकायचंय? हो हो. बर बर, मी बोलतो. Sorry. So the gas phase reactants deposit thin films or nanostructures on a substrate at high temperatures. Okay. Now you see titanium nitride nanostructures we can synthesize using the CVD, and that this method is used for the one-dimensional and three-dimensional. Now here the gas phase means, you see, you can understand this because the vapors, we generate vapors, and these are also, and through that vapors, in the vapors, the substrates are kept, and therefore the gas phase here initially, and if you heat it, it evaporates and touches to the, again means gas phase we have to change. Initially it is in vapor, then after the some gap, so these vapors will cool, and if we cool, then the phase is changed, and therefore the gas phase reactants react on the means and develops the thin films or nanostructures on a substrate, or nanostructures or on a substrate, you see, and develop the thin films at high temperatures. Very interesting. And this is the flow chart. Okay, this is the flow chart. Electrochemical deposition method. So this is also used for the one and two dimensional. Electrode is the titanium oxide. An application of this electrochemical reduction or oxidation to deposit titanium oxide from a solution. Now the flow chart for this is titanium dioxide synthesis using the electrochemical deposition, the preparation of electrolyte solution, and titanium tetrachloride in ethanol or water mix, electron deposition on cathode. So this titanium dioxide nanoparticles form so it form under the voltage. Now rinsing and drying, remove excess electrolyte, heat treatment, improve crystallinity, so this crystallinity at 400 degrees Celsius. Heat treatment improves the crystallinity. So this crystallinity, it improves Okay. Now see here the deposition. Okay. This is the anode and this is the cathode. So this is the TiO2 and this is the solution of TiO2 and ethanol. Voltage, okay. Electrophoretic deposition, that is the EPD method. This is used for 2 and 3D nanostructure. Graphene oxide thin films. Okay. Graphene oxide thin films. We can use this one. So here the geothin films, geocolloidal suspension is deposited under an electric field onto an electrode. This is the flow chart for this geo deposition using electrophoretic deposition. Now, geo suspension preparation: disperse geo in water or ethanol. Electrode setup: use conductive substrates or FTO or glass. Now we have to apply the electric field. Geo moves towards the electrode. Deposition and drying. Remove solvent and anneal at 200 degrees Celsius. See, this is the flow chart, pictorial diagram of this one, and how the material deposited on this. Okay, this is the nickel ions decorated geo. Hammer's method, and this is used for two-dimensional graphene oxide. Synthesis: graphite is oxidized using potassium permanganate and sulfuric acid exfoliated into graphene oxide. The flow chart for geosynthesis using Hammer's method. सर मी जरा टॉप मध्ये आहे ना, काय बोला बोला ना काय. 5 तारखेचं मी सांगतो, परंतु 5 तारीख म्हणजे जरा थोडीशी अडचणीची हो. हो, नाहीतर आता आलो नाही सर म्हटल्यावर तर आलोच असतो ना. हा बघा ना. नाहीतर तुम्ही म्हटल्यावर मला नाही म्हणायलाच अवघड जायला लागलं. तरी आपण संध्याकाळी बोलायचं का? Okay, this is the formation of geo here. Okay, this is the graphite oxidation. Add KMnO4 and sulfuric acid, graphite mix. Then the geo form, stirring at 50 degrees Celsius, and addition of H2O2 to stop reaction. Washing and centrifugation, remove unreacted species, drying and exfoliation, sonicate to obtain geo nanosheets. Interesting. This is the methodology here, how to synthesize the geo. See here, these geo nanosheets. This is the method. You can observe, you can study this one, and you can notice here the changes. Now you see the material in the beaker. Color phase is also changed. Now you see here, 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 okay. Cooling at room temperature, then the addition of more deionized distilled water, addition of hydrogen peroxide, that is S2O2, then the filtration, vacuum drying, and then store in sealed container, that is the graphene oxide. So this is the here. Now last method is the, and this method is unique method again, because why? This method is used to synthesize 0, 1, 2, and 3-dimensional materials. And therefore, this is a unique versatile method. Cobalt oxide, quantum dots, zinc oxide, and sulfide nanowires, graphene oxide nanosheets, bio means bismuth oxide nanosheets, manganese oxide nanoflex, and zinc sulfide nanosheets and nanotubes. Interesting. The flowchart of this is given here. Now, the flowchart for zinc oxide, titanium oxide synthesis using hydrothermal method. Preparation of precursors, zinc nitrate in aqueous solution, transfer to autoclave, that is the heat at 180 to 250 degrees Celsius for 12 to 24 hours, crystallization and growth, zinc oxide nanorods form, cooling, washing and drying, and purified product. Now this is the pictorial diagram of this one, stirring this, and now this is this one. Why hydrothermal method is being used? Okay. Now, this is the very unique, as I mentioned that one. Okay. Because this method is widely regarded as an advanced and highly effective technique for synthesizing 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional nanomaterials. Due to several key advantages over other synthesis methods. Okay, it has the several key advantages, and these are, because this is the widely utilized. Why? Because it is advanced method and therefore widely utilized method and highly effective technique for synthesizing this one, including means sol gel, co-precipitation, chemical vapor deposition, physical vapor deposition. Below are the reasons why the hydrothermal method is superior. Because it has the wide applicability for different nanostructures. 0-dimensional nanoparticles. Hydrothermal synthesis enables controlled nucleation and growth of nanodots or quantum dots. So, hydrothermal synthesis enables controlled nucleation and growth of nanorods and quantum dots, nanodots and quantum dots. This method, nucleation and growth of quantum and nanodots. Okay. Quantum dots and nanodots, very important. Means dot means zero dimensional. Hydrothermal synthesis has that capacity to control the nucleation and growth of nanodots and quantum dots. One-dimensional nanowires and nanorods means here one-dimensional, and nanotubes also. Anisotropic growth in hydrothermal conditions allows the formation of well-aligned nanorods, nanowires, or nanotubes. Okay. NR, NW, and NT means nanorods, nanowires, and nanotubes. Nanotubes, nanowires, and nanorods. Two-dimensional nanosheets means graphene oxide, molybdenum diselenide, MGens can be synthesized with controlled thickness. Three-dimensional hierarchical structures, complex architectures like flower-like, pore shell, and porous networks can be synthesized due to the self-assembly properties of hydrothermal reaction. Now, it gives the precise morphology and size control. The temperature ranging from 100 to 300 degrees Celsius, pressure reaction time, and precursor concentration can be precisely controlled, leading to highly uniform and reproducible nanostructures. Facilitates the anisotropic growth of nanostructures, crucial for advanced material applications. Eco-friendly and scalable, uses water or other green solvents, making it an environmentally friendly process compared to sol-gel, which may require toxic organic solvents or chemical vapor deposition or physical vapor deposition. Now, the scalability is excellent, allowing large-scale production of nanomaterials with low cost and high yield. Okay. High crystallinity and purity. So the hydrothermal process promotes the defect-free crystal growth due to this low reaction kinetics, leading to highly crystalline structures. In contrast, sol-gel and co-precipitation methods often require post-annealing, which may introduce defects or impurities. Okay. Sol-gel method and co-precipitation method outlines, define or elaborate these methods, how the defects and impurities. Synthesis of complex and multi-component nanomaterials. It allows for doping heterostructure formation and composite synthesis in a single step. Therefore, for example, tungsten carbide based manganese dioxide nickel doped cobalt oxide nanocomposites can be synthesized without multiple processing system. Energy efficient and low processing temperature. It requires the work at relatively low temperature compared to chemical vapor deposition, and PVD is greater than 500 degrees Celsius. Reduces energy consumption while all tunneling high quality material formation. It reduces energy consumption while enabling high quality material formation. Control surface chemistry for functional applications. Now it controls the surface chemistry for functional applications. Hydrothermal conditions allow for precise control over surface functionalization, which is important for supercapacitors, enhanced charge storage, photocatalysis, increased active surface sites, memristors, optimized defect engineering. So this method, which is important for synthesizing for tailoring or for fabricating these supercapacitors, photocatalysis, memristors, photosensitivity applications. Now prepare nanomaterials for the application of photocatalytic activity, antibacterial activity, sensor, photodetector, and supercapacitors. Now iron doped Bi2O3 published this paper. This paper was published in the Results in Chemistry journal. It's having the impact factor. Now these are the X-ray patterns, and you see of the pure bismuth oxide, then iron doped bismuth oxide 0.5%, 0.3%, and 0.7%. And these are the crystal structure of the samples. And these are means A is equal to B is equal to C. That is the cubic. And these are the lattice parameters, volume cell, dislocation density, which go on increasing and then suppresses. Its micro strain again calculated and stacking fault. And it is found that it is enhanced initially and little bit there is the minor change in this. Now the bismuth means pure bismuth oxide and doped bismuth oxide, and here you see this is the field emission scanning electron microscope of these, and you see the material nature on the surface. This is the photocatalytic activity of the as prepared, the 0 minute to 180 minute. See the plot. Here is the enhancement in absorbance. Enhancement at this. Okay. If we, and in somewhere, in some of the, okay. Photodegradation of methylene blue dye by pure Bi2O3, 0.3% iron doped Bi2O3, 0.5% this, 0.7% this. And this is the 0.7%. You see the change in absorbance. Now this is the plot of time versus C by C3 and plot of time versus log C0 by C1. And variation of the relative concentration of MB dye solution under visible light irradiation in the presence of pure Bi2O3 and 0.3, 0.5 and 0.7% iron doped bismuth oxide nanorods over 5 cycles. Now 5 cycles and what changes we noticed here, these are outlined. For 5%, you see the change. Here is the hello. हाँ एक 5 वाजता बोलायचं. Okay. And this is the, means here is the drastic change. You see, even though in this cycle, all this means at this 5 cycle, we noticed here that change. Now you see antimicrobial activity, and here what we found. So for this pure, the change antimicrobial activity of pure and iron doped Bi2O3 for different against bacillus bacteria and aspergillus flowers fungi. Okay, this is the fungi where 0.5% iron doped Bi2O3. Here the diameter of zone inhibition, what we found here for this and for this means diameter of zone inhibition in millimeter. Here is, you see, for this 0.5%, too much. Okay, so these are the means antimicrobial activity, and for this change area is covered. This one, you see, this is the area covered. This is the drastic change, and again here means bacillus bacteria and aspergillus. So aspergillus flowers fungi, and here is for 0.5. You see, this is the area covered, 23 in millimeter. Okay, this area more, and here is the 20 for bacillus bacteria. Now geo-based iron doped bismuth oxide. So this paper was published in Ceramic International, and its impact factor is this one. Now you see, these are the nanorods. Here we synthesized successfully. Okay. This is the stainless steel Teflon line autoclave. Stainless steel Teflon line autoclave. And this instrument means we design and directed to fabricate to the firm situated is in Pune. Now this is the XRD patterns. These are the peaks, okay, of Geo pure Bi2O3 and Geo, okay, means pure Bi2O3 and Geo 0.3, 0.5 and 0.7 iron doped Bi2O3, okay, means here Geo and pure Bi2O3, then Geo this one and iron Bi2O3, okay, and its dislocation density and crystalline size and volume, all these parameters we calculated. Now you see these are the field emission scanning electron microscope micrographs of Geo, and you see the formation of the somewhere structural parameters of this one. You see this, and these are the ADAX and how much percentage of this, okay, and these are the agglomerated nanoparticles. Here is the agglomeration found, and this is the time evaluation spectra of Congo red azo dye degradation and pure Bi2O3. So Geo and pure bismuth oxide, Geo and 0.3, 0.5, this is the iron bismuth oxide, Geo 0.5 bismuth oxide, Geo and 0.5% iron bismuth oxide, and Geo 0.7% iron, and this is the time evaluation spectra of this Congo, and this is the plot of time versus C by CO, okay, plot of time versus log this one, variation of the relative concentration of Congo red dye solution in the presence pure Bi2O3 and all these, and the comparison of photo degradation efficiency in percentage for 3 cycles, and this is given here. Now this is again the time of different, and here you see the effects of various scavengers on the photocatalytic degradation efficiency, and here is the effects of various scavengers on the photocatalytic degradation efficiency, MO and methylene orange and methylene blue mixed dye. Now Geo-based tin iron co-doped bismuth oxide nanocomposites, and this paper was published in Journal of Energy Storage. Its impact factor is 9.4. Now we came to this, the Geo-based tin iron. This work we have done and completed in the Advanced Material Research Laboratory, Department of Physics, Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhaji Nagar. And these are the XRD peaks, the patterns, and change we confirm here, the intensity here. So this is the pure, then the intensity enhanced. Okay. And here is the 30,000 angstrom unit intensity. And now, oh, here these are the field emission scanning electron micrographs. Here is agglomeration, but here is the some sheets. You see here, sheets are formed. Okay, nanoflex-like morphology. This sample shows. And now this is the CV curves of pure and 5% tin iron co-doped bismuth oxide. Okay. Now you see here what is the important. This is the galvanic charge discharge curve of all synthesized sample at 0.4 RNS per gram and the calculated capacitance of all samples with different scan rates. Okay, scan rate. Now you see here for this GO 5% tin iron bismuth oxide and the specific capacitance is 1300 and 2.5 and solution resistance is, you see here, decreased, and charge transfer resistance in ohm. Now you see here 0.3, drastic change. Charge transfer resistance. Resistance is reduced from 3.96 for pure and for this. And the specific capacitance, Faraday per gram, specific CS, it is enhanced, and this is notable change which will occur here for this 5%. Now you see 5%. This is the scan rate, and you see here this 5%. This is the voltage and time. Time. This is the voltage versus AG means electrode, different reference electrode. And experimental. Now here this change is noticed for this time, but the capacitance calculated here, that specific, and found that 1300 is quite interesting. Now this is the Nyquist plot and cyclic stability and Coulombic efficiency of synthesized samples. Now you see the capacitance retention and Coulombic efficiency. Here is exactly little bit suppression, but the Coulombic efficiency and capacitance is this one. And now, therefore, this is very interesting. Now, titanium doped cobalt oxide nanoparticles, and this work published in Materials Today Communication, impact factor is 3.1. Now the synthesis of this one, now you see degradation product. So here is this, these are the structural parameters of this titanium doped cobalt oxide. These are the XRD, yeah, crystallographic parameters. See, very interesting what we got here. You see, field emission scanning electron microscopy demonstrates the rods, and it means these are the nanorods, one-dimensional material. Nanosheets and nanorod-like morphology was found. Okay, here is a nanosheet and nanorods. Length is this one in nanometer. Highest for TCO3. This is the time study of the methylene blue degradation. Spectra of samples, these, okay. And the capacitance and plot of time versus log. The degradation efficiency and pseudo first rate constant of synthesized sample. Okay, pseudo first order rate constant K and degradation efficiency, which we found that is noticeable for TCO3, titanium cobalt oxide. 97.29. These are the scavengers. Now, GEO-based titanium doped cobalt oxide nanocomposites. This work published in Ceramic International. Its impact factor is this one. These are the XRD patterns and structure of all patterns, samples. Cubic volume means these are the crystallographic parameters also we calculated. Here very interesting. What is this? Efficient. Images of synthesized graphene oxide. This is the graphene oxide. Okay. See here. Titanium. This is a pure sample. Graphene oxide, pure cobalt oxide. This is the titanium doped. And here what we got? The length of this sheet. Which one? CO1. Means this one. Sheet. See, just like a slab. This is useful. We got photocatalytic activity also. Now it's quite difficult to cover all the things now, but I will highlight on this. The effect of a radical scavenger addition on photodegradation of MB and MO, methylene blue and methylene orange, mixed dye under sunlight over GTCO1 nanocomposite calculated by UVVIS. The first order pseudo rate constant and photocatalytic efficiency of GPCO, GTCO1 and GTCO3 nanocomposite. Now here for this sample, titanium, cobalt oxide, graphene, titanium, this one, we got the very interesting result, and that is the higher to this and higher to this again. This work also published in Material Science in Semiconductor Processing. Impact factor is 4.2. The graphene oxide based nickel doped MnO2 we synthesized and we got this nickel doped delta MnO2. XRD result indicates that all samples have monoclinic crystal structure with delta phase of MnO2. Okay. Now this very interesting. See here, PMO, GMO, GNMO1, all these here means these samples we synthesized means pure manganese oxide, graphene manganese oxide. This is the graphene nickel manganese oxide, graphene nickel manganese oxide, graphene nickel manganese oxide concentration. Here you can see and you can find here the very interesting flower-like structures, sir. Hello, sir. एक 5 वाजता बोलायचं सर. बर बर काय करा 5:15 पाठवा ना. सकाळी का काय करा खाली वडगावकर असतील त्यांना भेटा म्हणा, काही अडचण आली तुम्हाला मला सांगा. बर हा मग बघतो ना मी. बर 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 मी बघतो, सांगतो. ओके ओके ओके. Now here you can see the images of the materials we synthesized successfully and we got the flower-like structures, that is the nanoflex. Okay, you see. Fe same images of pure manganese oxide. This is, you see. Now see the change in B. Just like it turns when we, and you see the background is a graphene. Now in C again, this is the graphene nickel manganese oxide. Here it forms the structure again, you see, in D, and in E again the background when we. Now this is the cyclovoltagram, yes, cyclic voltammetry of all the samples, and here we calculated the galvanometric charge discharge. Charge discharge curves of galvanometric, that is the galvanostatic. Okay. And the specific capacitance of all as synthesized nanocomposite samples is what we found here. So this is the charge transfer. So in previous sample, it was the 0.3, but here you see 1 point means no that much change. And in the specific capacitance, it is also means 694. Whereas in the previous sample, we got the 1300 plus, and here is the half. So active electrodes, we synthesize this. And this is the reduced graphene oxide iron doped alpha MnO2. And this work was published in Journal of Energy Storage with impact factor 9.4. Here again, we got the nano wires. You see this structure, Fe same. Okay. This is the supercapacitor application. We can use this material. These are the XRDs of these samples. This is the reduced graphene oxide. And the lattice parameters we calculated and we got for this is a drastic change in nanocrystallite size. And you see these are the Fe same images. Somewhere we got the rods, agglomeration, and in this, the nanofleck, and these are the wires. Again here, the aspect ratio, particle size we got here. This is the cyclic volta. These are the cyclic voltagrams. Galvanostatic charge discharge curve of all samples at this. Plots of this one again. So here is the change notice, and that is this one in case of this specific capacitors. Our interest is that to enhance this value. Time dependent absorption spectra of this. Okay. And now the plots of time versus charge capacitance. Here is the nanorod. And this work also published in Journal of Material Science and Materials in Electronics with impact factor 9.4. Now you see this is the reference. This is the counter electrode. This is the reference electrode. And this is the working electrode. Okay. 3 electrodes are there. We got. These are the XRD patterns of TGO. This is the morphology, which we found the nano rod-like structure and nanospheres also. These are the cyclovoltagrams of these prepared sample. Galvanostatic charge discharge curve. So this is the EIS circuit fitting of curve electrodes in Na2SO4 electrolyte solution. And this one is the capacitance retention of TGO 3% iron nickel MnO2 sample. Here change is noticed at 3%. Now active electrode, these specific resistance and specific capacitance and resistance. Here is solution resistance, now these are the EIS circuit fitting of curve electrodes in 1 molar Na2SO4 electrolyte solution. Capacitance retention of TGO 3% iron nickel MnO2 sample. Active electrode, electrochemical parameters of as synthesized sample. Specific capacitance, that is the Faraday per gram, and this is the, here we noticed, for this is the highest, that is the titanium, GO, graphene oxide, iron, nickel, MnO2, and its specific means this charge transfer resistance is also, oh, okay. And this bilayer nickel doped tungsten modified GO or GO hybrid composites. The Journal of Material Science and Materials in Electronics. Counter electrode. Supercapacitor GO, the RGO. XRD patterns. Calculated crystallographic parameters of TC and prepared TGO. Nano hybrid composite. Lattice parameters. Crystallite size. These are the parameters for this. And see here the nanosheet. The nanosheet like morphology was found in case of the TC and TGO. Okay. RGO, reduced graphene oxide. See here. Very interesting. Cyclovoltammetric, that is the galvanostatic charge discharge curves of TC and TGO. This is the current density specific capacitance, and here we found the electrochemical impedance spectroscopic plots, EIS, that is. Electrochemical impedance spectroscopic plots. Now we calculated here the current density, specific capacitance, charge transfer resistance, and solution resistance of TC and TGO. Okay. Now you can see here. Okay. This is the tungsten. But no that much change. Specific capacitance is 185. Now future scope of advanced nanomaterials. Okay. The graphene functionalization and its applications. The graphene two-dimensional nanomaterial with exceptional electrical, thermal. Okay. electrical, thermal, mechanical properties play key role and is a key focus in cutting edge nanotechnology research. Okay. Electrical, thermal, and mechanical properties, two-dimensional nanomaterials, is a key focus in cutting-edge nanotechnology research. Functionalization of graphene by introducing heteroatoms, surface modifications, or hybrid structures enhances its applicability in various fields, including biomedical engineering, photo supercapacitors, solar cells, and water purification. The functionalization of graphene, introducing the heteroatom surface modifications or hybrid structures, photo supercapacitors, solar cells, and water purification. Below is the future scope of graphene functionalization in these domains. This is the graphene functionalization for biomedical engineering. So it can be, okay, the derivatives, GO, RGO, and functionalized graphene outlines biocompatibility, antibacterial properties, high surface area, and excellent electrical conductivity, making them promising materials for biomedical applications. Future scope, drug delivery, functionalized graphene-based nano carriers can be used for targeted drug delivery and controlled release. Graphene conjugated with polyethylene glycol or that is the chitosan, can enhance biocompatibility, biosensors, and diagnostics. Graphene-based electrochemical biosensors for real-time detection of diseases, cancer, diabetes, and viruses, etc. DNA functionalized graphene for genetic sensing applications, tissue engineering, and regenerative medicine. Graphene-based scaffolds for bone, neural, and muscle regeneration due to their excellent mechanical strength and conductivity. So, functionalized graphene coatings for biocompatible implants, for example, orthopedic and dental implants, antibacterial and antiviral coatings. Graphene oxide functionalized with silver, zinc oxide, copper oxide, copper for antimicrobial coatings in hospitals and medical devices. Now the graphene functionalization for solar cells. Graphene is the it has the high electrical conductivity and tunable work function, make it an ideal material for next generation photovoltaic devices. Functionalization of graphene enhances electron mobility, charge separation, and high absorption, leading to high efficiency solar cells. Means these are the functionalized graphene can be used because it has the high electrical conductivity and tunable work function. Therefore, it can be used for the high efficiency solar cells. Future scope, graphene perovskite solar cells, PSC. Graphene doped perovskite solar cells can improve electron transport and enhance efficiency. Functionalized graphene is whole transport layers, STLs, and electron transport layers in PCS can lead to stable and high performance solar cells, graphene in tandem solar cells, graphene silicon hybrid solar cells for enhanced stability and light absorption, graphene oxide hybrid solar cells for cost-effective, flexible photovoltaics. Now, graphene-based transport cutting electrodes, GTCS. Now, functionalized graphene can replace ITO based electrode. Okay, means indium titanate oxide for lightweight, bendable, and cost-effective solar panels. Okay, graphene-based transparent conducting electrodes, TCS, graphene quantum dots for light harvesting. So this GQDS can be used as sensitizers in dye-sensitized solar cells. Means what is DSSCS? Dye-sensitized solar cells for improved efficiency. Now, graphene functionalization for water purification. These are the applications. The graphene-based nanomaterials for excellent of adsorption, filtration, and antibacterial properties, making them ideal for advanced water purification technology. Okay, making them ideal. Very interesting. Filtration for advanced water purification technology. Graphene functionalized for water purification. Future scope. Graphene-based nanofiltration membranes. Functionalized graphene membranes with nanopores. Geo-based membranes. Okay. Now, for efficient desalination and removal of high metals, graphene enabled photocatalysis for wastewater treatment, graphene TiO2 or graphene ZNO composites for degradation of organic pollutants using solar-driven photocatalysis, graphene as an adsorbent for heavy metal removal, functionalization graphene with carboxyl or hydroxyl groups for enhanced adsorption of lead, arsenic, and mercury. Graphene-based antibacterial coatings for water filters. Graphene membranes functionalized with silver nanoparticles for bacterial inactivation in water filters. So self-cleaning and anti-fouling graphene-based filters. Graphene membranes with superhydrophobic and antibacterial properties can prevent biofouling and enhance filtration grade. Okay, with this, so I cover all these things. Thank you for patiently listening my talk. So other content is also there, but due to the time constraint, it is not possible to cover. But in next lecture, I will concentrate on another topic, because what we have done and what product we produced, and we got the patent of the same. But here the talk was scheduled for 2 lectures, and I covered maximum in this. Thank you very much for listening this talk patiently. I owe my sincere thanks to the director, Professor Dhanasri Mahajan Madam, and the assistant director, Professor Rafe sir, and the non-teaching and technical staff of this academic staff college, that is the Mission Malviya Teacher Training Center of Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhajinagar. Thank you very much.
Thank you, sir. So, on behalf of this entire group, my special and sincere thanks to our Controller of Examination, Director, Board of Exam and Evaluation of our university, Professor B.N. Dole, sir, for sparing his valuable time out of his hectic schedule, setting the tone of this event through his inaugural address as well as his brief lecture on advanced materials. So I'm really thankful to you, sir, on behalf of this entire group. And with the permission of Professor B.N. Dole, sir, I now declare that this technical session is over, and all of us we will gather tomorrow here at 2:15 p.m. tomorrow. Thanks a lot.
Thank you. Yeah, 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 remove here.